I grew up in the immediate post-Apollo aftermath. I'm just a little bit too young to have seen the Apollo landings. Grew up, reading science fiction and watching Star Trek, and I always knew I wanted to be involved in space, but I didn't think I was going to have to work on how to get there. That looked like a problem other people were solving. So I was programming computers when you program them with switches instead of with typing in on a keyboard or no keyboards. Went off and went to Caltech, and that was a great school for me. Feynman was still teaching a little special course for freshmen and sophomores that I got to sit in on. That was cool. Realized then that no matter how much money NASA did or didn't get, it was never getting me into space, or people like me. So I kind of gave up. You can't Me Too your way ahead of SpaceX. And betting that you're going to get there because SpaceX is going to make some catastrophic business error, that's not a winning bet so far. What could you do that would make SpaceX obsolete? Not do what they're doing, only better, because you're not going to do what they're doing, only better. And even if you are height of hubris, even if you are smarter and better than they are, they exist and they're entrenched in the market. I don't share Elon's vision that we're going to get 1 million people to Mars with chemical rockets. And it's not a thing that takes $1 billion to make. It's a box with some coils on it. Light it up, and 3 weeks later, you pass Jupiter.
We were talking about going to Mars in 9-ish months, and now you're talking about going all the way to Jupiter in weeks.
Yes.
There are basically 3 eras of new space. The first era was in the mid to late 90s, and that was with companies like Beale Aerospace, Rotary Rocket, Masten Space Systems, XCOR. It was the foundation work that other companies in the next era used for policy and for reusable rockets. The next era is the early 2000s to like 2010 or so, and that would be the formation of Blue Origin, SpaceX, Rocket Lab, and they used the first era to kind of build something great. And now we're in the third era, which we're calling commercial space. The third era is the solidification of everything. New space isn't going away anymore. This is here to stay. No single player can take it out. There aren't many people who were here for all 3 eras, but Jeff Greason is one of those people. He actually has done really amazing things back with policy and with building next generation vehicles, and he has an extreme passion for getting humanity living and working off planet as soon as humanly possible. This was the most fun I've had doing an interview in a long time, and I hope you enjoy. What an incredible resume, right? Before we get into your aerospace background, or maybe this is part of your aerospace background, you went to school at Caltech as an electrical engineer. How did all of that get started? Because you didn't go straight into aerospace.
No. Well, you have to, I grew up in the immediate post-Apollo aftermath. I'm just a little bit too young to have seen the Apollo landings. So, I grew up, reading science fiction and watching Star Trek, and so I always knew I wanted to be involved in space, but I didn't think I was going to have to work on how to get there. That looked like a problem other people were solving. The space shuttle was supposed to make space transportation too cheap to meter. So I always liked circuits. I was taking things apart and putting them back together from a very early age. And I thought there'll be plenty of jobs for electrical engineers in space. So I don't need to study rockets. That's going to be a done deal by the time I'm graduated. So I, got very involved in electronics very early. I was, building in a kind of a kit computer at a training program I was in when microprocessors first came out. So I was programming computers when you program them with switches instead of with typing in on a keyboard or no keyboards. And I kind of grew up with all that.
Is this like the Altair days, or is this like...
It was a computer called the ELF, which you built from popular electronics, printed the circuit boards in the magazine. You used them to make the masks, to make the PC boards, and soldered it up. A 4-bit processor.
Wait, what could you do on the computer? Was it just like blinking lights of like math?
Very little. It had 1 kilobit of memory, but you could the memory refreshed at a rate that was the same as the refresh rate on a television screen. So you could take the refresh signal going to the DRAM and modulate it and display it on a TV. So, I made a little very low res graphic of the Enterprise flying around on the screen in about 1976. I went off and went to Caltech, and that was a great school for me. I loved it. Feynman was still teaching a little special course for freshmen and sophomores that I got to sit in on. That was cool. And then to tie it back to space, right, in the fall of 1985, Caltech's attached to JPL. So there's a lot of NASA gossip flying around. Mm-hmm. And in the fall of 1985, somebody came in and said, "Hey, did you hear? They fished one of the solid rocket motors out of the ocean, and one of the O-rings was burned a third of the way through." And everybody was like, "Wow, that was incredibly lucky. That could have been a really bad day." Nobody said, "Gee, I hope they do something about that." It was obvious that you would do something about that. But it wasn't obvious. They didn't do something about that. And a few months after that, I come down from my dorm into the common room in the morning. Everybody's clustered around the TV, and what's going on? The space shuttle just blew up. And, an hour after that, they're showing the puff of smoke coming out of the O-ring inspection port. And we're all going, that looks like the O-rings, but that can't be. They already had that. They already found that problem. So it's kind of a funny story. People think, Feynman was so clever with the little demonstration of dropping the O-ring in the ice water because he figured out what was going on with the O-rings. That wasn't it. Everybody knew what was going on with the O-rings. He figured out how to make that information public without having to credit the informant who told him about it. Like, hey, by you drop the O-ring on TV and you see that it doesn't squeeze back, you can clearly show that there's a problem here. He didn't have to say, so-and-so from JPL told me that this was a problem you already knew about. So clever, but not in the way that people thought it was clever. About that time, it's like, well, number one, the Cold War defense drawdown is starting to happen, right? There's no jobs in aerospace. Everybody's laying everybody off. And meanwhile, it's like, well, okay, we were all counting on the shuttle to do space transportation. It's not going to happen, right? This thing's, so the way I put it is, I realized then that no matter how much money NASA did or didn't get, it was never getting me into space, or people like me, so, I kind of gave up, it's like, well, there's nothing I can do, right? But I stayed interested. And after I got out of Caltech, I joined, Usenet, the predecessor to the internet, the Sci.Space and Sci.Space.Science groups. People would say things and I'd say, how do you know that? And they'd say, well, I read it in such and such a book. So I go get the book. It was through that I heard about the Delta Clipper program, DCX, which really is the ground zero for reusable rocketry in the United States.
In the United States?
Yeah.
Was there other reusable rocketry throughout the world?
Funny story. Rockets started reusable. Like the X-1 rocket, that was reusable. The X-1 rocket descends directly from the first regeneratively fuel-cooled rocket ever built in the United States. The hobbyists at the American Rocket Society read Sanger's paper, which introduced regenerative cooling in 1935, just before the Germans came in, took over Austria, and classified all rocket work. And they read that paper and went, "Oh, we could build something like that." So they went out and built it. Then they went broke. Then World War II came, and they got a contract. And somebody said, "Can you make us an 8,000-pound thrust rocket engine?" And they said, "Sure." So they went out in the backyard and pulled out 4 of their 2,000-pound chambers that they'd been rusting since they closed the doors, strapped them together with literally plumber's tape, the metal tape with the holes punched in it that you use to attach your water heater to the wall, spray painted it black to cover up all the rust, and that became Black Betsy, the XLR-11, which is the engine that powered the X-1 and all of NASA's lifting bodies. And they were still pulling those engines, the same engines, out of museums that they put them in after the 50s to power the lifting bodies in the 60s because they were reusable rocket engines. It wasn't until the ICBM program that somebody had the bright idea that, if we didn't care if the engine lasted more than one mission, we could save some weight. And they started making the engines short-lived and reusable to get that last 10% of the weight out of the engine. So DCX is kind of the rebirth of modern reusable rocketry. But there were reusable rocket engines on the Mirage 3 that were used for takeoff and landing from short fields. That it took the smart guys who were on cost plus contracts to invent the concept of an expendable liquid rocket engine. Because it's hard. It's hard to make an engine that lasts exactly one mission without being sure that it will only last 0.9 missions. Right.
That makes
so
sense.
it's really hard. You have to test everything to an inch of its life to characterize the life so well that you can shave the margins so tightly that there's not one more gram to get out of the engine, because if you do, it will burn out a little early. It's really hard, and it's the kind of thing you would only do with a payload like a nuclear bomb that you don't want back.
Very much so. Do not want that.
You do not want it back. No return to sender. So, where was I? So blah, 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 DCX. I heard about DCX, and I went, this is a really cool sounding program. And they were doing it for an amount of money that by NASA standards, would not buy coffee, right? It was like $100 million program. That program was on the razor's edge of being canceled from day one. So I, like a lot of other people, went and visited my congressman for the first time and lobbied him, don't cancel this program, which was my introduction to political action. Mm-hmm. And then in 1994, there was going to be a conference in Phoenix that included a lot of the people I was corresponding with online, right? All people from the DCX program and other citizen lobbyists who'd gotten interested in the program, plus the subject matter experts that I was corresponding with. And I went, it's worth a vacation day. I'm going to go. And that was Space Access 1994, which is like Woodstock for the commercial space industry in the United States. I don't think anybody who started a commercial space company for the next 10 years wasn't at that conference. Mitch Clapp, Pat Bond, the guys at Kistler, the guys from what became Universal Space Lines, the guys from Rotary, the guys from HMX, the guys from AMROC were all there.
This is like the first wave of commercial space. Like, we think about SpaceX being commercial space, but they weren't the first wave, right? They kind of took over after the first wave.
I mean, the true first wave was the company run by that ex-astronaut. I'm blanking on the name of it. 1982. The first commercial space launch company. It's
not Beale. He wasn't.
No. It's God, I can't believe I'm not coming up with the name here. It wasn't P. Conrad. That was later. Deke Slayton.
Oh, okay.
And they did the first space launch company. It wasn't successful, but it's created the impetus for Ronald Reagan's executive order creating what became the Office of Commercial Space Transportation, which is now under the FAA. That was like, we got to have some kind of agency for licensing this kind of thing. Mm-hmm. But no, the big first flowering came out of that era. And I just went out of that going, I want to do that. I really care about that. I don't really care if Intel has 85 or 90% market share in CPUs next year.
I mean, it's in your blood. It's your passion. You've been doing this for, you went to school effectively to try to figure out how to do this.
Well, I went to
It's your
school thinking
lifetime.
other people would have figured it out by now.
We haven't.
Well,
We're getting closer.
We almost
We're getting closer.
We almost have.
Yeah. Mm-hmm.
Yeah, so I started driving down to Portland State University every weekend. I read every book in aerospace they had in the library. I read every issue of the Journal of Spacecraft and Rockets from Volume 1, Issue 1 up until the current issue. And a lot of people, that was a great way to get into it. A lot of people to this day are like, how do you know about this or that obscure road not taken, or technology that we can pull out for solving a modern problem? The answer is because I looked at the whole history of the field to figure out what I wanted to do. And in 1996, I gave a talk at that same conference that was still going on about the economics of various rocket propellants, which was not a subject you wouldn't believe the amount of research I had to do in the pre-internet era to even find out what the price of rocket propellants were. But, I went through all that. And Gary Hudson saw my talk there and pulled me aside and said, I'm looking for somebody who, is a experienced technical manager, but not from the aerospace cost plus world. And that's what I did at Intel, was manage technical projects. So, that's how I got to be recruited to be running the rocket engine development program at Rotary Rocket, even though I had no background in rocket engineering. And Intel had been a great training ground for that because for a combination of weird circumstances, I wound up being, like, by 20 years, the youngest guy in the room in the little steering committee we had about what are we going to include in each new generation of Intel's technology. What we're going to make $1 billion bet here. What technologies do we bet on? And that was great experience for how you manage that kind of programmatic risk and have a technology portfolio so that there's always backups if your bet doesn't pay off, that kind of thing. So Rotary was interesting. It was I'm doing all the talking here, so
keep going. This is great. I love it. Absolutely.
It was technically the concept was very out there. It was this helicopter with the rocket engines on the tips, and the mechanical power of that thrust is what turned the rotor, and that pushed on the air for the first 2 or 3 Mach numbers. And after that, it was just a big centrifugal pump because you were in thin enough air that it didn't really matter that it had rotor blades on it anymore. But the rotation of the G-forces of rotating the tip gives you this hydrostatic head. It really is like a centrifugal turbopump, just unusually big radius and unusually low RPM by turbopump standards. And it's mechanically powered not by having a turbine, but by the tips of the jets on the tips, which have just enough angle to provide the mechanical power, and most of their thrust is down. So it was a clever concept, and I looked at the numbers, and I had looked at something similar for rocket-driven propellers, looking for an engine that you could do point-to-point transport with, which is a field I'm still working on. And so I knew that the basic physics of it, I didn't know if the vehicle would work, but I knew the basic physics of this rotating engine concept were sound. By the time I got there, they'd already dropped that concept and gone to the engines on the base of the vehicle. And I could write a book, but I won't because, some of the people are still alive, about all the management disasters of that company. Let's just say failure of that company was preordained. Had, as one of my co-founders at XCOR said, the company had multiply redundant failure modes built in. But what it did is I had 2 years there with quite a lavish budget for the day to hire people, anybody I could find who knew what they were doing. And what I found is they're all dead. It's 1997. The last major rocket engine development program in the United States was the Space Shuttle main engine. I still remember hiring this guy, or interviewing this guy who had a great looking resume. It's hard to find a good looking resume in rockets. And he came in there, and his entire career, and I mean from the day he was hired to the day he retired at Rocketdyne, had been optimizing the shape of the turbopump housing for the Mark II high-pressure oxidizer turbopump assembly for the SSME, which is the version they never built. 30-year career working on the design of one piece that never got tested, never got built. He didn't know anything about anything. He wouldn't know which end of the rocket the fire came out of. It was just a good looking resume. And this was so classic of the kind of stovepiping of the giant human wave assault you got from the cost plus contractors in those days. I found a few very, very retired folks from the 50s. Not all of whom were way too old to consider coming back. Like we talked with, I'm blanking on his Max Hunter, who was the chief designer on the Thor missile. I found probably the last living guy who worked at Reaction Motors, which is the XLR-11 engines. And he had a attic. He was running a bait shop in Idaho. He had an attic full of original XLR-11 documentation. I have a copy of the user's manual for the XLR-11. But he was in his 80s. He wasn't coming back to work. So eventually what I wound up doing is just hiring, really bright people who had the knack for it. And we learned how to do it by reading the old reports and making mistakes again. So at the end of that, 2 years gone by, I get called in. Gary said, we're going another direction. We're not developing rocket engines anymore, because NASA's got this great rocket engine called the Fast Track that's going to solve all of our problems. If you know anything about the history of rocketry, that may have been the solution to something, but propulsion wasn't it. We all got laid off. Right. And what happened was, now I'm going to get through this without tearing up. The team called me in and said, okay, we're not ready to quit. What are you going to do now? So that became XCOR Aerospace. What do you do when you have what at that time is literally the only team in the U.S. who has current knowledge and, the dice are still hot in their hand. They know what they're doing on liquid rocket engines at a time when there's no market for liquid rocket engines and no industry to sell them into. So the answer was, what we have to do is find some market, however small, that you can serve with reusable rockets, which people don't even know reusable rockets are a thing.
Back then, they're not just not a thing; they're almost a laughingstock.
Oh yeah, I mean, NASA proved that reusable rockets can't work.
Engineer. It's so different today.
I know.
don't think people realize how different it is today.
Those words were said many times. Why are you bothering with reusable rockets? NASA proved they can't work. What you're trying to raise tens of millions of dollars. Everybody knows you can't build a rocket for less than $1 billion. Blah 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 blah. So, the market that we found was people. We think that there was a thought then, and I still think it's true, that there's a modest number of people that will pay to go to space just to pay to go to space. And they're self-loading payloads and they bring their own money with them. There's not a lot. I think the people who think this is a thousands of people a year market are kidding themselves. But I thought there'd probably be hundreds of people a year doing it. It was just based on simple analog stuff like 100 people a year pay to climb Mount Everest. It costs about $50,000. About 10% of the people who reach the top die. And 100% of the people who try are miserable. It's a terrible experience. And nevertheless, people will do it because they want to do this thing that people aren't able to do. But you have to have a per flight cost that's in the thousands of dollars to make money doing that. Right. It can't be $1 million a flight. It's got to be south of $10,000 a flight if you're going to make money serving that market. That was a big ask. We thought it was doable. And we made, if I may say so, I think we helped move the needle. XCOR was not a commercial success. Eventually we had one of the investors we brought in did kind of a hostile takeover from inside the company. We all got booted out. And then they managed the company into bankruptcy in very short order. Um, but along the way, we really did demonstrate that you can do high operational tempo reusable rockets. We did the Easy Rocket, which had a per flight cost of $900 for a piloted vehicle. Took about 4 people to turn around in about 4 hours. We did the Rocket Racer as a customer vehicle for a notionally paying external customer. A promise to pay external customer.
Now, was the external customer the Rocket Racing
Yes.
League itself? I don't know if people remember the Rocket Racing League.
Yeah, it was this outfit that had the idea that you could do a sporting event where you'd have a bunch of rocket powered vehicles flying around a kind of virtual course in the sky. And to make that work, kind of like watching car racing, the vehicles can't spend a lot of time on the ground. They need to be in the air a good chunk of the time. So that kind of started with a little study contract of, is it even possible to do a vehicle with a 10-minute turnaround? And I said, maybe. I mean, the Atlas in theory was ready to go from 10 minutes. So it might be possible. And they said, well, we'll give you a little study money to find out. So we did a little study money, and we develop fast fill techniques for liquid oxygen tank. And we filled a quarter scale LOX tank in a minute, and we said, okay, if we can fill the quarter scale LOX tank in a minute, we could probably turn the vehicle around in less than 10. And we did ultimately demonstrate, I think, 9 minutes and 11 seconds from pulling the chocks in to servicing the vehicle, to pulling the chocks out.
I want to pause for a moment. I don't know if people realize how impressive that is when you're working. This is cryogenic fuel.
Oh yeah, this is kerosene, LOX, and helium, as well as electrical power, all being serviced in under 10 minutes.
Yeah, so cryogenic valves and tubing does not like to move quickly. Just as a statement in general. So
yes.
This is kind of an incredible feat, and this is early 2000s?
Yes.
I mean, arguably still kind of ahead of its time even today.
I think so. Is it Tom Mueller, who he basically, we told him what our engine life was, and he said, "You're lying. You can't do that." It's like, well, we did. The fleet leader engines had about 600 life equivalent firings on them by the time that the program was done, and they were in brand new condition. We could have used them forever. We never wore an engine out. Our longest lived chamber went 2,000 firings before we retired it, because it was no longer, the design was so antiquated. It wasn't teaching us anything anymore, keeping it in service. Without getting into technical details that would bore the heck out of everybody, liquid rocket engines fail because of thermal cycling in the cooling jackets. And what we did was found a way to put mechanical compliance in the engine, so that as the liner expanded, instead of being constrained so that the tubes had to flex and bend, they had room to grow. So the engine was in its elastic range rather than plastic deformation range on every firing cycle. So in theory, they should last forever. Or at least millions of cycles, which is equivalent to forever. Valves still have a life, and they have to replace them every so often, and the seats, and the seals, cryogenic seals have life. But those are cheap parts to replace, so it just takes some labor. I really think and also what happened is, because of the results we were achieving when the industry was developing a regulatory picture, right? We anticipated that there would be a regulatory discussion, and we had planned on purpose. We knew the likely outcome was there's going to be a debate over when is it an airplane and regulated by the airplane people, and when is it a rocket and regulated by the rocket people. And we said, well, what'll happen is we're going to license the first vehicle we do as an experimental aircraft. And what'll happen is there'll be a big debate and a big argument. And when we're done, they will claim that the first vehicle was correctly licensed as an airplane, because that way nobody has to say they made a mistake. And they'll draw a new line for where the boundary is going to be that will be just above where that was. And that's exactly how it worked out. That became, and I had that all written down in a plan in my drawer, in a folder that was labeled the Space Precautionary Act, which is a reference to Heinlein and his story, The Man Who Sold the Moon. And in case anybody ever wanted to know how we do a regulatory system. And in 2003, Dana Rohrabacher's aide called me up and said, how can we help the commercial space launch industry? And I said, we need a regulatory reform. And he called me back next week and he said, I called 13 companies and 12 of them said, we need money. And you said, we need a regulatory reform. And Dana Rohrabacher is not on the appropriations committee, so he can't do anything about money. But he is on the authorizing committee, so he can do something about the regulatory reform. Let's talk. And that became, after much drama, the Commercial Space Launch Amendments Act of 2004, which created the regulatory regime for commercial human spaceflight under which we still operate today.
What was the reform needed? Was it that there was no regulation?
There was no regulatory structure for commercial human spaceflight at all. Human spaceflight had not been envisioned as a commercial activity when the first enabling legislation was done. And there was also no test flight regime available. There was no equivalent to an experimental aircraft for spaceflight, which incidentally, SpaceX made a strategic error in how it interacts with the regulatory regime by not taking advantage of that. They totally could, because the regulatory regime, the legal regime is in place there for you to do all your test flights under one piece of paper. And they didn't take advantage of it, so it's still lying there fallow for somebody else to do it. But Elon and I did not see eye to eye on that one. But anyway, the fight over that bill, which got very ugly among the then participants of the industry, it got to the point where dueling companies that had different representatives in the Senate or in the House were calling up their member to tell them to put this amendment in or that amendment, and we weren't talking to each other. So when the bill was passed, we said we should never do this again. We need a trade association, some mechanism by which we can have these debates behind closed doors and hammer out a consensus before we go in front of Congress. And that became the Commercial Spaceflight Federation, now Commercial Space Federation, which we founded on the card table in Elon's first building, when it was small enough that they were still working on a card table.
The one in El Segundo?
Yeah.
Yeah. All right. Yeah.
It was, you were just working on electronics, and there was this little glass sheltered corner in the back. And there was two folding tables in there, and that's where we created the Federation.
I think there's actually also a famous mariachi band picture from that where he's got, yeah.
So that I stayed involved in the regulatory arena to jump ahead, and that became the last involvement I had with that was what became the Commercial Space Competitiveness Act, I think of 2015. And that was all crafted through the Federation and went much more smoothly because we had a mechanism for doing pre-competitive coordination on matters of industry interest. There's various ways you have to structure yourself to be allowed to have a conversation among the industry legally without being accused of colluding for purposes of creating monopolies. There's antitrust requirements you have to meet in order to be able to have that. So the Federation does all of that, has all that legal structure, et cetera. There's your first question. What was your second question?
No, that was it was a great history of how you got from electrical engineering into aerospace, which I find interesting because I always thought of you as your passion being propulsion. And so I didn't expect to see a double E in your schooling, right?
My passion really is to get us off this rock.
Fair.
We are what's the line from The Great Escape? The first obligation of every prisoner of war is to try to escape. We are all born prisoners of gravity. We got to escape them.
Heck yeah, absolutely. So when we escape, because I think it's a question of when, not if at this point. I think
I'd love to say that's true. We are not. If Elon got hit by a bus tomorrow, I'm not confident we would make it. The now, mind you, let me be clear what I mean about that. Commercial space launch as an industry is now established. We aren't going back. It took the efforts of many people for a generation to break the Apollo mindset that the government is the way to go. Okay, that's been done. But the truth is, and this relates very much to this group that I'm now a part of that you want to talk about, is that the truth is, making an off-planet presence of some kind into a not money-losing endeavor takes an ecosystem. There's no one venture holds all the pieces of the supply chain. And the Elon answer of, well, we'll just fold all the pieces of the supply chain into the company only goes so far. So we're going to need an industry that has many complementary capabilities and pieces that form a complete ecosystem. And we don't have that right now. And as a result, much of the activity that you see is held up by speculative investment capital, which only lasts until they realize there might not be a market for it, or is held up by the whims of billionaires, which is great as long as they don't get hit by a bus or get married, or it's held up by government funding, which changes every 2 to 4 years as the whims of political tide and fortune change. So obviously we're in better shape now than we've ever been, right? Since 1950, every wave has gone a little farther up the beach. We're not over the seawall yet. We're in good shape, and all we have to do is not screw it up. But there's no guarantees of that. So I'm not triumphalist yet. The time to relax has not come. But obviously we're in way better shape than I could have dreamed of. We're in way better shape than I expected to be. But there's more to do.
There's still a lot more to do.
Still a lot more to do.
You mentioned investment, and it's a really interesting thing right now because I think you're right. Like you look at a SpaceX or you look at any one of the commercial space companies, right? They're doing a great job. And we've got tons of rocket companies, and you see investors look at the success of SpaceX, which is, I don't know its current valuation. I think it's like 1.7 trillion or 1.5.
They're hoping it's over $1 trillion. That's
it's they'll immediately be one of the most valuable companies just immediately. And so as an investor, where investors are looking at that going, oh, I want to do that. I'm going to build a rocket company too. And the problem is we have so many rocket companies now.
Yes.
We have so many rocket companies now. We don't need more rocket companies.
Yeah. I get asked, do you want to do something like XCOR again? And like, heck no. It made sense in 1999 to try to raise money to show that a tiny investment could find a tiny market to prove that reusable rockets were a thing. We don't need to prove that anymore. Everybody knows that now. Well, everybody but ESA knows that now. I
don't know. SLS isn't reusable either.
Well,
let's be fair. Vulcan?
Let's not concern ourselves with the non-market economies. But yeah, we don't need the 147th rocket company. The nature of chemical rockets is that they take a large capital cost to build a large vehicle. And then that capital cost is amortized over ideally lots and lots and lots of flights. That's what makes it cheap. And what that means is there's enormous economies of scale inherent in transportation with liquid rockets. So there's not going to be very many successful companies because whoever happens to have most of the market is going to have the lowest price. So there's a feedback cycle that tends towards larger entrants. Now there's countervailing forces. Nobody likes having a monopoly supplier. People will cheerfully pay a higher price to the number 2 or number 3 provider, just to make sure that they aren't beholden to the number 1 provider. So there's going to be a number 1 and what I call 2.5. There'll be 2 market leading companies and a handful of smaller ones that are looking for little niches to break in. And that's going to be the state of liquid rocket transportation until we find a different technology for going to orbit. And I'm working on that. That has different economics, that's on a different cost curve. That's the nature of the game. We don't need 147 rocket companies. Number 1, almost all of them are going to fail with no reflection on them whatsoever. Maybe they're great people with a great team and a great idea. It's too late. The first mover has moved. You can't Me Too your way ahead of SpaceX. And betting that you're going to get there because SpaceX is going to make some catastrophic business error, that's not a winning bet so far. So if you want to compete in space launch, which I think is still possible, you have to do what I call skating to where the puck is going. You have to ask yourself, what could you do that would make SpaceX obsolete? Not do what they're doing, only better, because you're not going to do what they're doing, only better. And even if you are height of hubris, even if you are smarter and better than they are, they exist and they're entrenched in the market. So don't try to do what I call charging up the beach into the machine guns. Go somewhere else. Go where they're not. So I think there might be a pony there, but the bigger opportunity is to look at all the other pieces of the value chain besides Earth orbit transportation.
This is a tricky thing for an investor. Sorry to interrupt.
No.
It's a tricky thing for an investor because they see the success of SpaceX. I don't know if they have anyone to tell them, hey, SpaceX only gets us this far.
Yeah.
There's everything after it that still needs to be built. Don't you want to be the SpaceX of the next thing, which isn't the rocket?
Yes, it's very difficult. And to be honest, we haven't done very well. This is an area where there's a gap, right? Companies get started as if they are going to exist in isolation. Nobody wants to hear in your investment pitch, I'm building this company on the assumption that 4 other companies that don't currently exist are going to be founded and become successful, and they'll be the customers for my product. And there was a time when we looked to government to perform this architectural role. They had a vision for where systems were going, and it had some predictability, and if the Army was building a post in a frontier state or territory that currently was unsettled, you could go to your bank and say, I want to start a farm there, and I'm going to sell my produce to the Army post. Because nobody assumes the Army's not going to be there tomorrow. Right. And the railroad could say, I'm going to route my stuff through there because there's already an Army post there. And there's already farms there. I can feed my passengers, and things grow up from there. And in the 50s or 60s, you had NASA performing this kind of vision. We don't really have, caveat. I haven't watched today's NASA announcement yet. So maybe I'm 2 hours behind the times, but we haven't had a clear vision that isn't just of the present state, but is of the future state, where people who are starting new ventures can see how they would plug in. And so the group, you probably actually know what it's called. I don't. The group that I'm part of that,
the Pathway to the Cosmos?
Yes. Is attempting to see, can that gap be filled privately? Can we map out the critical steps in the chain, the pieces of the ecosystem, and take that around to investment sources and say, maybe instead of just investing in the 147th rocket company, you should look at where the gaps are in this chart. Those are the opportunities that are currently uncapitalized and also currently lack any established entrant or competitor. You can be the first mover, if you go into one of the blank spaces in the chart. And I think there's value in that, because I think the investment world might not know what they should do, but they are getting the sense that what they're doing probably isn't the right thing.
So, you talked about things. So for those who don't know, we're actually recording this on March 24th. And earlier this morning, NASA gave a large update as to their vision for lunar exploration. And they're hyper focused on the moon. I don't necessarily disagree with that. I think there's an incredible cis-lunar economy. And I'm of the opinion that going straight to Mars doesn't make a whole lot of sense.
We're not ready.
I agree.
It's not that it's a good or a bad idea, but we're not ready. The trip times that are involved with chemical propulsion are so long. We don't know how to keep people healthy and alive on those kind of durations. I mean, I'm not saying you couldn't do it once, but you couldn't do it as a routine thing right now unless certain lucky breaks happen to roll our way. It totally does not make sense to we haven't kept somebody alive in Earth orbit for 2 years. Clearly, if you're going to start doing those kinds of longer and longer duration experience, it makes sense to do that while evacuation is a possibility. We don't know about the gravity. We don't really know how much shielding it takes to get long-term health from cosmic rays. I'm not saying these are barriers. They're not things that you go, it drives me crazy when people post stuff like on Twitter, well, you could never go to Mars because of X, Y, and Z. It's like, believe it or not, we've thought of that. But the fact that we thought about it and we know there are alternatives doesn't mean that we're ready to do the mission design tomorrow. We need the equivalent for going to Mars of what Project Gemini was for going to the moon. We need to build up the length and duration and competency in doing these kinds of operations. We need to resolve some unknowns. It makes perfect sense to do those in cis-lunar space. Plus, one thing you have to do if you're talking about human settlement and not just an expedition for the National Geographic or something, you're going to have imports. They're not going to be zero. There have to be exports to pay for the imports. Well, it's really hard to think of things you can export from Mars to the Earth. It's not really hard to think of things you can export from the moon to the Earth or to customers in Earth orbit. So those not so people, for some reason, people get turned off when you talk about profit and loss. I don't understand it, but profit is nature's way of telling you you're doing something smart. But these things have to get paid for. If we're not looking to government to do them, they're going to be paid for privately. If they're going to be paid for privately, somebody somewhere thinks they're going to make a buck. There's nothing wrong with that. Recognize that that's the grain of the wood and work with the grain, not against it. So I'm not centric to any one destination in the solar system or beyond. I want to do it all. The reason why you think of me as mostly working in propulsion is the common element. Right. Every destination has its own challenges, but there's not one of them where getting there faster and cheaper wouldn't be helpful.
Oh yeah.
Plus, it turns out that propulsion and energy are almost the same problem in two disguises. And energy is the other thing you're going to need everywhere you go. And thinking about how you do advanced propulsion and how you get advanced energy are, again, two facets of the same problem. So I can work on all of that stuff. Go ahead.
Before we get into propulsion, because I definitely want to talk about that too, because we have I don't know if people realize how difficult it is to get out of our gravity well here on Earth, and we need a revolution there as well. We need a revolution in a lot of these things. I do want to talk about finance because it is so important, and I think you're right. A lot of people poo-poo it, but if you don't have finances, you don't have a program. It's just going to be an idea is great. Cool. It's an idea. But if you can't fund it, you can't build it. And if you can't keep it funded, then it just gets added to the graveyard of the million companies that came before it. And so finance is absolutely critical to figuring all of this stuff out. So it is a large part of the pathway to the cosmos of like helping investors understand you don't need another rocket company. I can't tell you how many, we don't need another rocket company. But here are places you can invest. And we're talking about propulsion, but what outside of rockets, like what are some other areas that we need? I know we need all of it, but like, I don't know if people are thinking about this stuff. So what else do we need to live and work in space?
Okay, specifically, so you mean we'll put propulsion aside for now and talk about the non-propulsion aspects.
Yeah, I want to dig really deep into propulsion. So we'll just pin that for a moment. Then I want to loop back to propulsion, really go into what that means.
So back up one further and ask, what are you trying to do? Right. One of the problems we've had in the space arena for a long time is a lack of clarity about what do we think, what's our win condition, right? What is our goal? What is this it that we're trying to do? I think we have not progressed so far as a group that we have an approved mission statement or goal for the group. Okay, the group is still forming, so take this entirely as me, but I think we're looking for successful human settlement at more, initially one, but eventually many places off the Earth, right? And there are many reasons for that, right? You can think about that as insurance. You can think about that as a venue for the development of new kinds of human societies, because you can't risk developing new kinds of societies if you only have one, right? Because most attempts to build new societies don't work. You don't want to screw with the one you got. You want to do those experiments in other venues. What we used to call a frontier. You can go off and try and fail, and we know most of those are going to fail, but sometimes the successes will be glorious and it's worth it. I worry a little bit about human freedom, right? That the natural tendency is, as transportation and communications improve, the size of a political unit enlarges. We're really at the point right now where we're debating, is there room for two economic and political structures on the planet Earth, or is there only room for one? There's not room for dozens. And as transportation continues to improve and communications continue to improve, the pressure to consolidate is just going to grow. So everybody has their own reasons why they want what's been called a multiplanetary. I don't like that term because I don't know if planetary surfaces are or aren't going to turn out to be a big deal. Because we don't know the answer to how much gravity it takes to stay healthy. If the answer turns out to be a sixth, planetary surfaces are going to be a big deal. If the answer turns out to be 80%, planetary surfaces are not going to wind up being a big deal. And we don't know the answer to that question yet. But a multipolar world, where there's many centers of human civilization, it's polycentric, means you have redundancy. It means you have diversity. It means you have new kinds of opportunities for trade and interchange, new ways for ideas to move back and forth, and it means you have room to let people try things and fail, because it's not your only egg in the basket. Okay, what does that mean? What is a human settlement? Okay, well, you've got people somewhere. They have access to energy and stuff that they can use to build and expand their habitat, and also to build products of some kind, which can be exported to pay for whatever it is they have to import, so that they are economically, self-sufficient. They don't depend on somebody writing them a charitable check every year just to keep going. Okay, those are the big dogs then, right? You need people. People are expensive right now. Why are people expensive? Because our life support technologies are unbelievably primitive. Right? You wouldn't believe. We aren't recycling carbon at all. Right? You send food up to the International Space Station, you eat it, you exhale carbon dioxide, which you then store. That's the one pass through and done. The ISS is the first time the US has recycled water. which we go through a lot of,
Mm-hmm.
right? So there's been progress, but it's been glacially slow because, can you imagine what all the barriers are and all the meetings you'd have to go through before you could take a new piece of life support equipment up to the International Space Station and actually plug it into the life support environment? All the international partners would have to agree. Um,
But wait, that's changing.
it's
That's
changing.
changing because we've got Axiom, we've got VAST.
Yes.
And so as an investor, you're
There's
completely right.
absolutely
There's a life
opportunities
support.
now for improved life support. That's one of the big dogs. Closure of the food loop is difficult. Right? There's several ways to go about doing it. You can do closed agriculture of some kind. You can do what I call vat culture, where you're growing microorganisms that you're going to harvest for food elements. Or you can do what's called physiochemical things. Like there are certain foodstuffs you can actually make from chemical feedstocks that you can make from CO2 in the air. You can make fats that way, essentially.
That's good because right now I think I have to eat bugs if I want to. Right?
And
that.
observe,
well, I mean, no,
right?
Right now today maybe.
This is part of the things that drives me crazy that people don't get. Like, why would we spend money in space? Like, look, you could say it's possible to demonstrate all these kind of closed loop things on the Earth. You could say that, but people will not do it because they don't have to do it. Right? That you need a first adopter for all these technologies. In space, these supplies are expensive. It's worth investing money to start closing your life support system. But once we know how to do it, there's absolutely no reason why those technologies won't become applied on the Earth and we can induce the environmental footprint it takes to keep a human being alive here. It just drives me crazy. Every problem that we face in space is solving urgently a problem which we will eventually have to solve somewhat less urgently here on Earth. Why on Earth? Why would we not start doing that? Right? The energy is the same thing. It's like people can have argued till they're blue in the face. And I don't even have to get into a position. I don't have to have an opinion about how dangerous CO2 is or isn't to be emitting in the atmosphere. What I can tell you is diplomats can negotiate until they're blue in the face, and we can sign treaties until you could stand on them and reach the moon. And it's not going to make one bit of difference on how much CO2 we emit. If you want to emit less CO2, you have to present people with a technology that makes the energy with less CO2 for the same price or cheaper. Otherwise, they won't do it. Well, guess what? There's no oil on the moon. If you want energy, it's going to be solar or nuclear. Those are the only games in town. We're going to have to learn how to make those cheaper. This has positive implications for wherever you're going to be. So we've talked about life support. We've talked about energy. You have to be able to expand your habitat space. That's a much less trivial problem than it sounds because, the environment you live in has to be built. And if you're depending on agriculture to close your food loop, you really need quite a large area. You need like a quarter acre to an acre of habitat space per person to keep the crops that are growing that it takes to keep that person alive. So it's the habitat space that you need is potentially very large. It has to be cheap to make. That means they're not aluminum cans that got made by an aerospace contractor in Italy that you launch one at a time. You're going to have to make these things from the materials that are at hand. How you do that as a technology. Gee, do you think cheap habitats made from tissue materials we can find other uses for? I'm sure we can find other uses for them. But again, the first adopters, which, it's much easier to establish those technologies when somebody has no alternative. You have to learn how to make these things from the local materials because that's all you've got. And then really the big one that we haven't talked about is transportation and energy. But energy we've touched on. But life support, habitat, and materials. That's the other one. You have to be able to acquire material. Believe it or not everything in the universe that we use is made of software, although the guys in Silicon Valley haven't quite figured that out yet. I'm old enough to remember when Silicon Valley meant hardware. The we make stuff that you could drop on your foot, stuff made of atoms. You're going to need a source of atoms. Um, Even if we wind up with most of the people living in free space, if it turns out the gravity requirements are that stringent, then that just means that you need even more atoms. So they have to come from somewhere. So you need industries to gather material and process it into useful forms, that you can make the things out of that you need to make, and that you can sell either as a finished material, like oxygen, or turn into some manufactured product that is part of your export trade. And then you need propulsion to move all this stuff around, because you don't get anywhere without propulsion.
So, and let's talk on propulsion now. But all of the things that you just mentioned, I would argue, are just as valuable, if not more valuable, than what SpaceX has built.
Oh yeah. I mean, can you imagine what would happen if you perfected a process for providing 50% of the calories that somebody needs in a vat the size of a 55-gallon drum? I mean, there are people who think they can do that. Everybody could have one. You wouldn't need agriculture anymore.
and none of this is science fiction. This is all real stuff that just needs a little bit of a push into space. And once we get it into space, it opens up all of the opportunities here.
Yes.
It is truly the pathway to humans living and working in the cosmos.
Yes.
And the way I like to look at it is, today, all of our money for space is spent on Earth.
Yes.
But the future we're talking about is we will have humans living in space, spending money in space.
Yes.
That's the difference.
And
that's the key
why
differentiator.
People are essential. Only people generate demand. Robots don't make demands yet. So yet. if you have 20 people living on the moon, there's going to be a chef. There's going to be a bar. There's going to be service industries that have to be met. Those people are going to have free time. They're going to need something to do with it. They're going to have access to materials and energy. If you now think of a new product that needs to be made and you don't have, and it would never pay for your new product to establish a moon base and get 20 people up there. But it would pay for your product will pay just fine if you can get 5 hours a week from the spare time of somebody who's already there to make one more thing. That's the thing about the space economy that people do not get. The hard part is getting to this threshold where there is an economy that includes some consumers who are not on the Earth. Because once you are there, the incremental investment to add a new product or service to that economy is tiny compared to what it took to get there in the first place. It's almost like the economics of software. The reason why the investors like software so much is once you make the product, the cost of sales for one more unit is nothing. Well, once you have a functioning space economy, the cost of capital to create one more new product or service is almost nothing.
Let's talk propulsion.
Okay.
Because
I can talk about that until you run out of time.
There is no, I'm going to listen. This has been great. I'm going to let you go for as long as you want to go. This is, we haven't had a huge advancement. We've had some advancements in propulsion, certainly. I don't want to say we haven't had any.
No, you can say we haven't had any. It's true. The liquid rockets were developed conceptually in 1902. They were developed as a functioning device, in the 1930s. And they were essentially perfected by 1960. And all that's happened since then is some people like me have worked on improving the life, and some people like SpaceX have worked on improving the thrust of weight. And some people have worked on improving the chamber pressure, and those are all incremental improvements that you'd expect from a mature technology. But, it's a mature technology. There's no new magic to have in liquid rockets, and there never will be, because we understand chemistry pretty well. We know what energy you can get out of various combinations of elements on the periodic table. Rockets now operate at something like 98% plus of their theoretical maximum efficiency. you can get to 99, but that's a 1% improvement. So there's the game changing stuff. Now, what people see as the big improvement is what people were saying, a few visionary people were saying back in the 60s. Rockets have this economy of scale. So if you want to make the price come down, you have to get more and more and more flights out of them, right? And so that's finally happening at last. Thank you, SpaceX. Thank you for your efforts.
I will, going back, I think it's everyone. I think SpaceX stands on the shoulders of those before, right?
Or trots on the corpses, yes.
It was NASA too. Well, a little bit, but like, it's not like, there's a lot to it, right?
There is, but so Elon filled in the two critical missing pieces, which was he was able to talk people into giving enough money. You could actually build an orbital system, which is a significant capital investment that nobody else had been able to put together. Even then, it came within a hair's breadth of not being enough, but it got there. And the critical innovation of putting the satellite company under the same roof as the rocket company, so you have the self-licking ice cream cone. You can generate your own demand because the entire rest of the industry put together doesn't generate enough demand to keep even a first stage reusable system busy. And when people think about Starship, it just amuses me. For years, people have been asking me technically, what about this risk that Starship faces? What about that risk that Starship faces? And I'm like, it doesn't matter. I may agree or disagree with technical approaches that are being taken, but if they're right, they'll work, and if they're wrong, they'll change their mind. What matters is, does the money keep coming in, right? So what matters is, can he continue to convince people that there is a market for 100-fold increase in the traffic of Earth to orbit launch? If there is, they'll keep giving him money. If he doesn't run out of money, it'll eventually finish. If there's not, it doesn't matter how brilliant technically it is, because it's too big for the market and it will be a commercial failure. And then none of this has anything to do with the things that people natter on about technically. It's not a technical problem.
Most of space is a financial problem.
Beyond that, there are things to do, right? I'll pass very lightly over Earth orbit, in part because I don't want this to be a commercial for stuff that I'm working on, and in part because it's competition sensitive. But broadly speaking, Earth orbit is hard for chemical propellants. The energy of being in orbit, just the kinetic energy being in orbit, is like 13 kilograms of dynamite being set off for every kilogram that you put into orbit. It's a lot of energy.
I don't think most people can relate to the stick of dynamite metric, though. I don't think I go, oh, how much energy does a stick of dynamite have?
About 5 megajoules per kilogram. So,
it's a lot. For every pound on Earth, or for every kilogram on Earth, you need substantially more in just fuels and everything else.
Right, and that's what drives that's why rockets are such a giant piece of hardware, and that's why they cost a lot of money to build a factory for, because building big things costs more money than building little things. And, the cost of the propellant is not anything to do with it. It's the cost of all the machinery it takes to build all that equipment and move it around the country and all the rest of that stuff. So if you want to change that, you got to do something that has dramatically lower ratio between the mass of propellant and the mass of your payload. And there are possible avenues to that. Broadly speaking, what I say is you can help from the bottom, or you can help from the top. There are various forms of ground assistance that you could do. You can do beams, you can do catapults, you can do the launcher assistance of your choice, or you can breathe air, right? Those are all ways of getting help for the first few kilometers per second. And you can help from the top. You can put an orbiting beam asset that sends power to the vehicle to help do the last couple of kilometers per second, or you can put an actual beam that pushes, and you can use the mass of the station that the beam is mounted on as a reaction mass to push the craft the rest of the way to orbit. Or you can literally do an arrestor hook. You can come up and mate with a hook that yanks a pole cable out of the station, and gets the last 2 kilometers a second by yanking the reel out. But it only works for like the last 2 kilometers a second or so. On the other hand, if you got your first 2 kilometers a second from the ground and you got your last 2 kilometers a second from orbit, you now only need 4 kilometers a second instead of 8. And you'd only need a mass ratio of like 3, which is almost airplane-like. So the vehicle that went in the middle would be the payload mass fraction, the fraction of the vehicle that's sitting on there that actually paid to be there, would be much more airplane-like. And if the traffic is there, that's always the question. Is there enough traffic to keep that system busy? And without getting into it, one of the things I'm working on is, can we use a system like that to do surface-to-surface transport cheaply enough that it competes economically with subsonic aircraft?
When you say surface to surface, do you mean point to point on Earth?
Yes.
Or surface of Earth to Moon?
No, point to point on the Earth. Because, the whole global space launch market is tens of billions of dollars, but the global air transport market is $1 trillion. So if you could crack the global air transport market, you'd have a system that could go to space on evenings and weekends, for airline-like economics, because the airlines would be paying for the factories and the airplanes and the people and the overhead. So that's one approach.
You were talking earlier about how everything in space has an application back here on Earth, and here's an application for propulsion. As someone who has to fly to Australia from time to time from Florida,
in the
United States, let me tell you how badly I want point-to-point travel. Making some assumptions, anywhere on the planet in 90 minutes or less.
Yeah.
Right? Like, I'll pay for that. I will absolutely pay for that.
The sad truth is, though, people say they'd pay for that, but they don't pay. They wouldn't pay very much for that. The number of seats you could sell if it was 5 times the price of a subsonic ticket would not be enough to make the vehicle worth building.
Well, I would pay 5 times
perhaps,
it depends on the ticket. I would not pay 5 times a first class ticket. Next time you fly,
look back at all those people in coach. They're paying for the plane. The people sitting up in the front aren't paying for the plane. So it's a brutal business, and it's technically a very difficult ask. And I'm not sure the problem can be solved, but I'm working on it, because if it could be solved, it'd be interesting.
It sounds like a fun problem.
It is a fun
problem.
Also,
I personally just selfishly want you to solve it so I can get to Australia in 90 minutes or less.
Understandable.
So working point to point, is this really only a Earth gravity assist system, or is there applications outside of our gravity wells as well?
Well, if you put some kind of assisting structure in orbit, a station, it's a very natural extension for several of the technologies to say, once you're there, you transfer to another vehicle and that station pushes you away, and you get the first 2 kilometers a second or so of going where you're going from that assistance platform. Broadly speaking, off-Earth transportation is there's Cis-lunar and there's everything else. Cis-lunar, the distances are so short. It's really a hard problem to come up with a dramatically better than rocket solution, because you don't have time to build up significantly higher velocities. I've tried to make the numbers work for an electric tug to go to and from lunar orbit for 30 years. Never works, because the spacecraft is slow. It takes time to get there. Yes, you need less mass to do it because it's using the mass more efficiently, but it takes more time, and it's an expensive asset, and you don't get enough round trips out of it before the bank wants their money back. So it's hard to make the numbers close. I do have one little wrinkle that's looking interesting, but it's better talked about when I talk about it in the context of, here's a beyond Cis-lunar thing that might have a Cis-lunar application. So the real big dog in Cis-lunar is to get propellants off the moon, right? The moon is about 40% oxygen by weight. The kicker rock, it's made of various metal oxides. So it's not a question of polar volatiles that are they're incredibly interesting, but we don't really know what the quantity of those is. The moon is not going to run out of oxygen. So we could be exporting oxygen off the moon at prodigious rates for centuries and centuries and centuries. Actually, probably for a lot longer than that. And oxygen is, a good chunk of the mass of rocket propellant. Somewhere between about 3/4 and about 5/6, depending on what you're burning for your fuel, of your rocket propellant is oxygen. So picking oxygen up from the moon and shipping it back downhill to Leo to fuel a chemical rocket that goes to and from the moon is a great way to lower the cost of Earth-Moon transportation. The moon has no atmosphere, which is awkward. It means you have to pay to get down as well as to get up. There are ways to get around that. There are tether type systems. It's like a science fictional space elevator, but it's way easier to build on the moon than it would ever be on the Earth. And the lack of atmosphere is a help, because you don't have to worry about dragging it through thunderstorms or anything like that. And the gravity is lower. You can build that out of materials that exist today. It's a thing. You can build that out of steel. You don't need, old unobtainium.
So would the solution be from Earth to a Earth orbiting station and then Aldrin cycler over to like a space elevator and then elevator down to the moon?
Could be. Earth-Moon cyclers are kind of iffy whether they're that interesting. If you have a station on both ends already, the velocity you're saving is not very significant. It really comes down to, do you need a lot of shielding for the people? Then it might make sense to keep the shielding moving and move the people to and from the shielded volume. But we're barring solar storms. The trip to the moon is so short, we're really not worried about it.
I push back slightly.
Okay.
I feel like barring solar storms is hand-waving away the entire sun.
The nice thing is solar storms you can shield against with a much more reasonable amount of mass. So you can the radiation involved is high in quantity but low in energy. So we haven't historically shielded our spacecraft about that. We've just forecast solar weather and cross our fingers very firmly. But unlike the problem is galactic cosmic radiation, the shielding problem is so difficult that if you want to make a significant dent, you're talking about an amount of mass that is a large multiple of the mass of the spacecraft. Shielding against solar storms is absolutely a thing for which your design consideration has to be done, but it's doable. So that's why I put it in a different category.
Is this where we do better space weather prediction and just try not to launch through a solar storm?
Could be. That it's probably not an all of the other answer. You probably have a storm shelter, a little minimum space that everybody could crowd into, for solar storms below certain thresholds, and above certain thresholds you don't fly, just like you don't take off into a thunderstorm. It's a question of, how good is your prediction? How much margin? You're done with numbers. So the other thing I'll mention is an idea I'm fond of on the lunar surface is what I call the dust fountain. The one thing you have plenty of on the lunar surface is dust. Well, if you pick it up and throw it, because it's an airless body, it goes quite a long way. If you ran into a cloud of dust that was being thrown up from the surface, it would be like running into an atmosphere. You could brake against it. So you can get most of the delta V of getting down to the lunar surface that way for a quite modest piece of equipment on the lunar surface that throws the dust up in front of where your spacecraft is going.
I have never heard. That is a really interesting idea. I've never heard it before. The first place my brain goes is regolith isn't like dust. Regolith is sharp.
It is.
Like
It is.
It's, I mean, you're gonna, but then again, if you're hitting metal and you're not hitting like rubber seals and things like that,
No,
it's
you
not
have to
that
have a
sharp.
strike plate on the front of the
Yeah.
spacecraft to do that. But it's not a hypervelocity impact. Lunar, when people are used to like the dramatic pictures of the meteor protection on ISS, where this little grain of sand makes this great big hole. That's because the sand is coming in faster than the speed of sound of the metal. So the metal can't get out of the way. Lunar orbit is not that fast. So it's more like sandblasting than it is like a hypervelocity impact. You need a strike plate, but it would abrade at a reasonable rate, I think. I haven't published it yet because I haven't had a customer for it. So free to go home. Okay. Other than that, I have nothing clever to say about cislunar transportation, and I'm ready to go on to the rest of the universe.
Let's do it because, like, I do think like I said earlier, I'm in the moon first camp, but I'm not in the only moon
Right.
camp. Like I want us to go to Mars. I want us to go to Enceladus. I want us to go out in the universe. I want us to go to other star systems. But we've got a problem with chemical rockets in that just going to Mars is going to be around 6 to 9 months, probably
Each
closer
way.
to 9.
Yeah.
Each way, and you got to wait for the orbits to
Yeah.
realign. It's so long.
Yeah, this is for
It's
the
so
birds.
long.
I'm not saying we'll never do it, or I'm not, but I don't share Elon's vision that we're going to get 1 million people to Mars with chemical rockets.
So how do we do it?
Boy, okay. So let's see. I turned my 3-day class into a 3-hour class, and I turned it into a 3-minute class. I don't know.
Give me a 3-hour class. I mean, if you've got time, like what do we do? This is a big deal.
It is.
Like
Okay,
this could forever change things. How do we, this is opening up the universe to everyone.
Broadly speaking, right, you can classify propulsion systems in terms of where do you get your energy and where do you get your momentum from, i.e., what do you push on? Rockets are the conceptually simplest system because the answer to both questions is it's in your propellant tank. The propellant carries its own energy and it forms your reaction mass that you throw out the back. So it's not surprising that we started with that first because that's the simplest way to go about the problem. But as you quickly run into the fact that chemicals only have so much energy, and we've got what there is to get, and the only possibilities that are out there for something better along those lines involve propellants that are so spooky. I'm not going to write on them. They're high energy monopropellants that can go off by themselves, or make incredibly noxious chemicals when they spill, or there are reasons we don't use them. So what is there? Broadly speaking, one class that's interesting is to beam the energy and carry the reaction mass. Right now you can use higher exhaust velocities because what limits them is how much energy you have available to accelerate the reaction mass. We can, our various ideas for advanced onboard power, like nuclear thermal or nuclear electric systems, run into the problem that nuclear reactors are fairly heavy. So there is absolutely improvements to be made there, but they're not jaw-dropping. And the reason being that the way that the reactor has to be carried, and that's a problem. If you beam the energy, you can leave the reactor home. You can collect energy from whatever source you're collecting all the rest of your civilization's energy from, and beam it to the craft. And there are you can do that with a laser, or you can do that with an electron beam. Lasers take big optics if you want to go a long distance. But they're easy to receive. Electron beams.
We're talking about the universe, so can you define long distance? Because like the scale here is crazy.
If you wanted to do a laser rocket to Mars, you'd like the laser to go at least about 1/10 of an astronomical unit. The astronomical unit is the distance the Earth is from the sun. Mm-hmm. So then you have a nice long runway to build up some speed with, and you don't need a ridiculously high-powered laser, and you buy lasers by the watt, so you don't want to have to have ridiculously high-powered laser. That takes like kilometer optics, which are inconvenient to build on the ground, but would be pretty easy to build in space, because it'd be a big thin film Fresnel lens that you would just print out. So it's not crazy. It's interesting. It's doable. It's not my favorite, but there are people who are working on that for whom it is their favorite. And I'm an all, I am not against any form of advanced propulsion. As long as it'll work, I'm in favor. So that's one class of approaches. Another class of approaches that I'm extremely personally interested in doesn't really have a name. They're generally speaking interactions that you do between the vehicle and the plasmas that are the background medium in space. In one of the forums I'm on, that class of systems is being called plasmadynes. But that's not a widely accepted term yet. It's just, you have to have a name for a thing that you call them. So space is full of something. Space is not empty. It's just that the stuff it's full of is extremely thinly spread. But the good news is the stuff it's full of is called a plasma. It's a form of matter in which the ions and the atoms are not ions and the electrons are not attached to each other. They're floating around free, which means you can interact with that plasma with electric and magnetic fields rather than by putting out a physical sail. The solar wind leaves the sun at 400 kilometers per second. Voyager leaves the sun at 20 kilometers a second. So there's a wind right now blowing out from the solar system, including past the Earth, that's 20 times faster than the fastest thing ever made by humans. Mm-hmm. All you have to do is grab it and you're leaving town real fast. So that's one method.
Do we know how to grab it?
We do. There's two good ways published, one not so good way published, and I'm working on a fourth. They're not proven in space, and you always have to be a little careful with these plasma things. They don't always work in real world the way they work on paper. But it would be an incredibly wise use of funds to try some of these out, because you could fly a CubeSat and prove these things out, and poof, we can fly 20 times faster. And it's not a thing that takes $1 billion to make. It's a box with some coils on it. There was a paper that I published with some coworkers, for a little demonstration mission that would be solar powered. So you would have to do all your acceleration in close to the sun. It was a 16U CubeSat. So it was about a 20 kilogram object. And the idea was you'd light it up and 3 weeks later you'd pass Jupiter.
Oh, wow. I mean, let's put that back in perspective, right? We were talking about going to Mars in 9-ish months.
Yes.
And now you're talking about going all the way to Jupiter in weeks.
Yes. So, okay, that works if you want to go away from the sun. But obviously, that's not the only direction we want to go. Going to Mars fast is mostly a prograde retrograde. You want to go forward in the orbital direction or backwards in the orbital direction more than you want to go in or out from the sun. Okay, but you have this big wind. If you could extract power from that wind, you could use that power to drive the electric rocket of your choosing. And it would be like having a nuclear reactor, only the nuclear reactor is the sun, and the solar wind carries that power to you to be used. And that looks incredibly promising. I am one of the co-authors on a paper on that. That gets you a round trip to Neptune, you could do a 1-year round trip mission to Neptune.
Okay, so hang on, I gotta wrap my brain around this. Okay, hang on. So we're talking about using electric engines in space,
yes,
which traditionally don't have a lot of power,
right? Because they're limited by the power supply, not because we can't make bigger engines.
Okay. Okay.
There's lots of ideas for how to make bigger engines, but nobody's working on it because where do you get the power from?
Okay.
Um,
Uh, but one of the advantages, as I understand it, is you're basically pressing on the accelerator the entire time, right?
it could
So,
be.
oh, you don't have to.
No, but if your problem is you're sucking power through a straw,
Hmm.
then you want to be sucking on the straw as long as you can. It's again a limitation of the power supply that makes you maneuver that way, not a limitation of the thrust producing mechanism.
There is an advantage to constantly being at thrust, which means you're creating an artificial gravity. Effectively, you're pushing everything against.
Yeah, the solar system is by most standards kind of big. It turns out that in interplanetary travel, like a hundredth of a G is a lot.
Oh,
So the if you could get a hundredth of a G, I mean, people in electric propulsion today measure their acceleration in millimeters per second squared, not in meters per second squared. So you say, I'm going to give you 100 millimeters per second squared. They're like, well, that's science fictional. And that's only a hundredth of a G. So,
yeah. So
uh,
fair enough. So that doesn't really actually help you
it
that
doesn't
much,
really
which
help. And
goes back.
it's wasteful of propellant to do that maneuver, right? If you think about accelerating to the halfway point and then decelerating, you're at your peak velocity for zero time, but you
Oh,
paid
yeah.
all the propellant that it takes to get to that peak velocity. So in practice, it's usually more optimal to thrust for like a quarter of the time, coast for half the time, and thrust for a quarter of the time.
Can you collect the plasma energy effectively and store it for
No, we
the
don't. If we had a
thrust?
way to store that energy that densely, we do Project Hail Mary. We don't have a way of storing that energy, but you can collect it the whole time and use it the whole time. The only thing is you can't collect it when you're too close to a planet because the planets make a wake that stops the solar wind.
Hmm.
So on Earth, you got to get out a good chunk of the way to the moon before you're in the wind. Um, the moon actually passes through the lee of the wind, which is why the moon is a little brown. The Earth's atmosphere, we lose a little of the atmosphere into the magnetotail of the Earth. It gets sputtered out by the solar wind. So there's oxygen ions streaming away from the Earth downwind, and the moon passes through that for a few days every month, which is why the surface of the moon is slightly rusty. It's from oxygen from the Earth combining with the iron on the surface of the moon that makes that dirty brown color that it shows up when the astronauts are looking at it. Everyone thinks it's gray, but that's because we're looking at it compared to everything else. Um,
Hmm.
so,
So
um,
you can get us, in theory, we could get to the end of our solar system in about a
in
year.
about a year. Yeah, it's you get to the Kuiper Belt in about a year. Um, the
This is a big deal. This changes
Oh
wait, hang
yeah,
on. But
and the
what,
mass ratio would be like for the round trip to Neptune. The mass ratio is like 2.5. So it's like a satellite or an airplane, not like a rocket.
hmm,
And for Mars, I'm still working on it. Mars is tougher because it's all prograde retrograde that you need to get no help at all from going outward and inward. So I'm not there yet, but my hope, my goal is a 6 month round trip to Mars. Um, that
round trip.
round trip, 2 months
So
there,
that's
2 months on the surface, 2 months home, because we keep people alive on the ISS for 6 months all the time. If we could do a 6 month trip to Mars, we could go tomorrow. The plus it would solve the waiting 2 years to come around again because you'd be able to do that trip like 8 months out of the year. So there'd be a bad time to do it, but most time you wouldn't have the Martian. You wouldn't ever have this thing of we have to wait a year before we can launch the next mission, which I think is a really heavy ask for the early people going to Mars.
the 4 months you can't do it. Is that when Earth Mars alignment has the sun in between? Is that kind of
No,
a
it's when they're kind of at right angles. Uh,
mm,
but it's related to that problem. It's that Mars is going to get to be on the wrong side of the sun while you're on the way of going to it. So
okay?
your trajectory that connects the dots would wind up going through the sun. Um,
So If we can get to Neptune in a year, how long would it take to get to, I almost said our nearest star, but that's literally our soul. But how long would it take to get to the next star
Okay,
system
that
over?
wouldn't be that method I just mentioned by itself wouldn't be practical.
We're still talking like well over human lifetime
Yes,
sort of thing?
yes. That fast by solar system standards is not fast by interstellar standards. Um, the the 400 kilometers a second is still only like, well, even 600 kilometers a second is only like 0.2% of the speed of light. So it's still just too slow. I will touch on some of the options. There is a boundary shock at the edge of the solar system, the helioshock, where the solar wind abruptly slows down. And if you've ever seen a bird skimming back and forth in the wind over the ground and like doing a loop that's one way on the ground, then it picks up speed when it comes into the wind, comes back down to the ground. That's called dynamic soaring. You can transfer energy if you have access to a wind gradient. You can pull velocity from the fast region and turn around in the slow region, and you can bounce back and forth off of that until you get tired of doing it. People have flown model sailplanes, radio controlled model sailplanes that way, up to almost the speed of sound, just by pumping their velocity up by flying up and down a hill. I've with some co-authors at the University of McGill. Yeah, we published a paper that showed you could use these kind of windmill propeller techniques of interacting with the medium to get up to about 2% of the speed of light for free. It takes about a year to do the acceleration. That's still not enough, but we're getting there. Mm-hmm. You can, once you're in the interstellar medium, right? The medium is sort of at rest. It's practically stationary with respect to the stars. So if you get launched in at some velocity, you feel a headwind, right? Because you're flying through this medium. Yep. You can now play this trick of extracting energy from that wind with a windmill, wind energy extraction device, and powering your electric rocket. And you can get about 4 times whatever velocity you started with. So if you start at 2% of the speed of light, you can get to 8%. If you start with 10%, you can get to 40%. Okay. So the name of the game is to start with as much as you can. Okay. So 8% still not enough. You need about 20% before you're in the ballpark. There are at least 2 ways to get from 2% to 8%. And 8% times 4 is fast enough. The one way is you can use sun pressure. You can eject these carbon puffballs in close to the sun, and the sunlight will push them away at about 2% the speed of light. And now you have the stream of carbon puffballs going off into the cosmos. You let them push you until you're at 2%. Now you're overtaking them. You can push on them as you pass. And it's like having steps or a cog railway. You use them as the reaction mass. And because it's going so fast, you also can go so fast. You can pick up about 8% of the speed of light that way. That's published.
I'm mentally liking it to like those nuclear pusher plates that they kind of did. Is it similar to that, where you're kind of pushing against a plate with a blast sort of thing? Like you're
when you're first getting started,
and then pushing against it.
It's like that, but that only works until you're up at the pellet speed. Once you want to go faster than the pellets, what you're doing instead is you use the windmill to pull energy from the wind that's passing by you. And you push on the slow thing. right? Imagine I'm going 3% of the speed of light and I have a stream of pellets going 2%.
Mm-hmm.
I feel a wind at 3% of the speed of light, but I think the pellets are only passing me at 1% of the speed of light. So if I take energy from the wind and I push on the pellets, it's energetically favorable because I only have to slow the wind down a little bit to get the kinetic energy that uses to speed the pellet up by a lot. We call that wind pellet shear sailing. And then yet another method is, I mentioned earlier that these electron beams, in principle, hold themselves together. The way that works is, again, the space plasma has these diffuse ions in it. If the electrons are going close to the speed of light, they see from these passing ions a current. And that current is, in the frame of reference of the electrons, looks like a magnetic field. And that magnetic field tends to push the electron beam together. And at the right radius, that balances the tendency of the electron beam to blow itself apart from its own self-repulsion. That's called a pinched relativistic electron beam. And we do this in particle accelerators all the time. It's not just theoretical. But the theoretical part is, can you hold it together over these immense distances? Because if you run the numbers, it should hold together for like 1,000 AU. And what gives me some hope is we look out into the cosmos, and you've probably seen pictures of these astrophysical jets, like galaxies with these big streams coming out the pole.
Sure.
Those are relativistic particle beams. And they hold themselves together in space, some of them, for like 100,000 light years. So there's some reason to hope. If you can see it in nature, there's reason to hope we can figure out how to do it. The part on that is not well worked out is how do you receive that power and convert it efficiently without melting the ship? So it's not all done. There's a lot of work left to do. It's frustrating to me that currently there's no source of support for this work. All this work is being done privately by people who are able to afford a hobby. It's people have this myth that NASA supports this kind of thing. They don't. NASA only funds advanced technology that's required for a funded NASA mission. And incidentally, your chances of getting your mission funded are approximately zero if it requires as yet unproven technology. As you can see, this is a loop that's very difficult to get out of.
We were joking beforehand. I think I said something similar along the lines of you can't fly non-space proven hardware until it's proven in space.
Yes.
But you're not allowed to fly it in space.
Yes.
Because it's not space proven.
Well, but see, that one we can get out of now because private people can prove it and then government can use it. But there's not a lot of customers for going to Alpha Centauri just yet. Or going to Neptune.
We don't need to go straight there. It's steps, right?
Yes.
Like we don't go straight to Alpha Centauri.
Right.
We go to the moon,
Yes.
right? That's the first step. Then we go to Mars and we make it suck less going to Mars. And then let's keep going.
Yes.
Why are we stopping at Mars?
Yes.
Let's keep going.
So, I mean, I really do think if we could scrape up, tens of millions of dollars a year for funding of various experiments and these kinds of things, you and I, or at least you, could live to see the first probe launched to another star. I don't think in our lifetimes we'll see a manned mission. But that's okay. We got a lot of work to do figuring out how to keep people alive for 30 years with radiation shielding and lightweight habitats and closed loop life support and all the things we need to prove before you can get people living over a long time on the moon or on Mars or in a free space habitat. Again, these problems all link together. So it's all part of the same enterprise.
100%, right? Like if you solve just the propulsion problem, then you have all of the other problems still.
Yes.
Like, cool, you've solved propulsion, but we still, what are we going to do with it?
Yes.
If you solve the radiation problem, but you don't have propulsion, cool, what are we going to do with it?
Exactly.
If you solve the water problem, but you don't have propulsion and you don't have radiation, Well, I mean, it goes in radiation, but like, cool, what are you going to do with it?
Yes.
Everything needs everything else.
Yes.
And one of the things that you brought up that we hadn't really thought of, which I thought was really clever, is like, it's not just solving these problems, it's also there's an order of operations to these things. You don't necessarily need to solve, X before you've done B or, whatever the case may be.
One of the things I really like what I'm hearing in the last few weeks out of the new NASA administrator is very much an emphasis towards before we start the 20-year, $100 billion program, why don't we do something else smaller and fast?
Mm-hmm.
There's a lot to be said for that because, you know, you there's always a spectrum between, well, we'll just try everything and we won't think about anything ahead of time. That's probably not the right answer. But there's also the spectrum of, well, we'll just think about it until it's perfect. Well, guess what? You can think about it forever and it will never be perfect. There will always be the things that you didn't think of. So there's a spectrum of, you know, how experimental and how theoretical are you? And the answer isn't at either extreme, but it's a lot more experimental than has been the norm in the space arena for a long time.
So, what do you need to build this next generation propulsion? Is it really just like a few tens of millions of dollars a year sort of thing?
Yeah.
Do you need a team? Like
Well,
what?
I
I mean,
do,
that
but
goes into all of it.
you could find. I mean, there's a community of researchers out there from which one could draw. You know, like putting any team together. Sometimes the most credentialed person is not doesn't work and play well with others. So you got to be selective about what you do. If I could have my dream, we would find a philanthropic source rather than a for-profit source who would found, a small research institute that got the researchers to try out some of these very high payoff but speculative ideas. And then, the funder of that would have first look at whatever came up with, and they'd have the opportunity to say, I want to take this into the for-profit side because I think that idea is now something that I can make a company that makes money out of. And we'd go, great, thank you very much. And we go back to working on the other four ideas.
I think that's a realistic thing. I think there is a potential business. Like, I think you could do that. It's just finding the right people. And, in part, that's kind of what the pathway is trying to do is get a group of people together so we can figure out the funding side of this, the people side of this, because people are part of the equation too. Like,
Absolutely.
None of this happens without people, right? So finding the right people almost harder than funding. Like you need exceptional people, and it's all of the tools and making sure that all of these pieces go together because there's a lot that makes this happen. And we started by saying, oh yeah, I really thought of you as the propulsion guy, but after just sitting here talking with you, your propulsion is really just because you really, really, truly want to see humanity get out to the stars. And it's not I really with you for someone like me it's like, oh, I'm happy if we make it to the moon, like I will be ecstatic. I think you're like I don't want to put words in your mouth, but it feels like you're like no, that's where we start on the moon.
That is correct, and I'll say why that's correct. Okay, the norm in the human experience for the last 100,000 years has been that we are a polycentric culture. We are not just one culture. And, we've been going to Europe and learning to sail the coasts and finding our way to Australia, and then the Polynesians figured out how to go across the Pacific. That's all part of the same story. Right? And it's only in the last, really, almost since World War II, that we've had this hard to put words in, but factually correct sense of the planet's not big enough for that anymore. It's really not. Our supply chains are global. We depend on products that are made in countries most people can't find on a map. And they depend on us. I I used to have to work hard to explain this to people, but I think the COVID pandemic showed everybody what I'm talking about, right? There's a flu in China and now I can't get toilet paper. What happened?
Yep.
Okay. So what's going on is we've discovered a new thing in that period, since World War II, since container shipping, and since the airplane. We've discovered that there is such a thing as your technology, your communication, your transportation being too good, right? Because past a certain point, it really does make sense to source something from the other side of the planet because it's 10 cents cheaper. Okay. And we get tremendous benefits from that, right? We don't want to wind the clock back. We don't want to go back to the age of sail. Our living standards would crash. Okay. So we don't want to go back, but we also don't want to lose the advantages of a polycentric civilization. So we need to spread out. But the problem is that's not a once and done thing. Because right now the moon is expensive to get to and difficult. But we already talked about things we could do that could bring that cost down 100-fold, right? The moon is close. It's in real-time communication with the Earth. When transportation gets cheap enough, the moon won't have to have closed loops life support and all the rest of these things we talked about anymore if they don't want it, because they could just afford to import things from what they're exporting. They don't need to be there's no insurance anymore. The insurance policy that you thought you'd get by being polycentric is gone. Now the Earth Moon system is one civilization again. Okay, by the time that happens, we have to have someplace farther. But we already talked about ways that you can get the round trip to Mars fast and cheap and painless. So we have to go someplace farther. Okay, well, all civilizations are powered by energy. Energy gets more and more difficult the farther you get from the sun. It's hard, even though Titan is a very interesting place to think about putting people. It's the only body in the solar system you can walk around on without a spacesuit. It's dark. It's going to be a very challenging energy problem. It's hard to see how you'd have a civilization there without an enormous amount of infrastructure. And the outer solar system will be scientifically interesting. I'm sure we'll find things to do out there. But once you get far enough from the sun, the next good spot to go is the next sun over. Then I'll die and you'll die and this will all be forgotten. And someday somebody's going to figure out FTL and the stars won't be far enough. That's okay. That's a problem we can leave for the people who follow us. But yeah, the name of the game is not to use the current phrase. It's not one more Hail Mary pass. The name of the game is to switch back to what used to be the human norm, that there's always a next place to go. There's always a new set of settlements and civilizations being founded. That's okay. That's no threat to you. You can let that happen. There's always crazies who have this weird idea about human liberty and the rights of man and all the rest of this crazy nonsense. We can just let them go off and try that stuff somewhere else, and they're all going to die anyway. What difference does it make? But sometimes they don't.
This is very exciting. I'm excited for this future. I'm excited to be able to look up at night and see a civilization on the moon, see the lights in the dark portion of the moon, right? And I think that's in our lifetime. I really do.
I don't know if you can see I think it moved. It's called The Lights of Home.
Yeah. Yeah, that. I want to look up and see that on the moon. And I really do think that's within our lifetime. And I want to bring you on the show. I could talk to you for hours. I could truly talk to you for hours. I also want to get into, not on today's, but like, there's a pathway that gets us here. Like, people don't realize none of this stuff just happens first time out of the gate. You have to go through very difficult, hard lessons that frankly suck to get to this point. And Like I feel like a lot of those lessons have been learned, and we're this close. We just kind of have to make the choice as a society, as a species, to push just a little bit harder. And I think we can enable
Where
something.
the wave is almost over the seawall.
Almost. We're so close. We can still screw it up though. We can not to be pessimistic, but like we have to choose to make this
No,
happen. We can still make it
can
happen.
you imagine how bad it would be to have come this close and blow it?
I certainly hope we don't. I really don't. Um, I'm going to bring you back on the show sometime. I do want to end. I have 5 questions we ask all of our guests, and we ask every time because it's interesting. Sometimes when we bring on guests, the answers change, and so I always enjoy that. But yeah, 5 questions for every guest, and these are kind of rapid fire. So, first one is, what is your favorite rocket or space vehicle, and why?
It's the Mirage 3, which is an aircraft. It's the most produced reusable rocket ever. They made hundreds and hundreds of them. And one of the variants of it came with a liquid rocket built in for short field takeoff and landing. And it's a very obscure rocket today, very clever little design, powered off the jet engine. And people were flying. That's a reusable rocket that was in operational service for 30 years. And nobody knows about it.
I had no idea. I'm going to look up the Mirage 3 after
It's
the
a
show.
French fighter.
Okay. What is your favorite planet and why?
Probably Titan.
Ooh, how come?
Because it's the only body in the solar system other than Earth you can walk around with in a spacesuit. It's got enough atmosphere. It's got enough radiation shielding. It's cold as heck, so you'd need one heck of an Arctic survival suit, and you'd need an oxygen mask. But I think we're going to find that planetary operations in pressure suits are an ongoing nuisance. And it would be cool to have at least one more place where you could go where you didn't have to do that.
I'm a Minnesotan. I'll be fine. I'm a Floridian now, so I would not. When do you think humanity will first step foot on Mars?
About 10 years after we get our boots back on the moon.
Okay. So if you had a rough guess, about 20 years from now, you think?
Well, I'm hoping it's not 10 more years till we get boots back on the moon.
It may not
I mean,
be.
they're talking about 2028, 2030 for that. So
yeah, and that actually seems reasonable. It seems achievable.
It's absolutely achievable. Whether the organizations and institutions we have will achieve it, I don't know. But for years we've been in the situation where a $5 billion prize would get a private entity back to the moon.
5 billion, yeah. And that was we'll talk about this next time I have you on. But the era of the X Prize challenges, right? The Ansari X Prize, the Google Lunar X Prize, all of those. That kind of goes back to I think kind of the tail end of Space 1.0. Or commercial space 1.0. It was really interesting time. It was really interesting. We could do it in just an entire show talking about all space 1.0. I think commercial space 1.0 because it was truly fascinating, and it's what got us here.
Mm-hmm.
It was a necessary step to get us here, and I don't think anyone realizes Beale Aerospace, as an example. I don't think people realize SpaceX is literally the testing site for SpaceX in McGregor.
Yes.
That tripod was not built by SpaceX. Yes. It was built by Beale.
Yes.
Yeah.
Yes. Andy was there early. There's at least 2 people I know of who are putting books together about that era right now. It's underdocumented.
It really, and it's a totally fascinating time. What is your favorite song and why?
I will give 2 answers to that. Pink Floyd's Time, because the lyrics of that always remind me to get going again. And there's a very obscure folk song called Mundane's Waltz by Leslie Fish. That is, I won't try to reproduce it, but you can find it if you Google carefully enough on YouTube.
My last question is, what draws you to space?
I have good answers to that. I've given some of them in the course of this talk. But I'll be honest. They're all post facto. They're rationalizations. They're things that I have come to by my research searching for the reasons that underpin what is ultimately a feeling. And I can't answer the question because I've never not had the feeling. It's just, it's like jazz. If you have to ask, you're never going to understand.
That is a great answer. I love that. Listen, thank you so much for your time today. This has been absolutely incredible. I'm really excited. First off, I'm really excited to have you on the pathway. It's I haven't been this excited about space in a long time. I remember being very excited about space when I joined SpaceX, well over a decade ago. Not that I fell out of love with it, but like it becomes.
Well, it solved the problem we needed solving.
Yeah.
That's great. It's solved. Now what?
Now what? And I think this is the now what. And I'm excited to be on this journey with you.
Very good. Well, I'm glad that I hope your viewers find elements of this entertaining and instructive. And if we get to talk again, that would be great.
We're going to bring Jeff back on at a later date so that we can ask follow-up questions with regards to how his next generation propulsion is going. Now, I am an engineer, but that only goes so far. I'm not a propulsion engineer. But if you've got technical questions you'd like to ask him on how any of this works or how any of this is even possible that I just didn't have the foresight to ask, leave it in a comment below and make sure to like, subscribe, and do all of the YouTube-y and things that we need to do in this day and age so that we can actually combat the algorithm and get this bubbled up. Because I think a lot of people need to hear Jeff's story, and I think we need to get him the tools necessary to get humanity to Jupiter in 3 weeks.
We're geologists here, astrophysicists too, and plain old hard workers like those in our crew. With one thing in common, we yearn for the stars, and we will not stop building until they're all ours.